carry on. So I talked about our agenda, and so the last part there is the stump the maintainer. If you have some questions, you don't really have to stump the maintainer, but if you have some interesting questions, please feel free to ask them in the chat along the way, but we'll get them. That's just the dedicated time to answer questions, and we will get them answered for y'all as part of the meeting. Okay, let's carry on. Next is the Linkerd Community Anchor Program. So just a couple of announcements. This is something that we love to talk about at every meeting to remind you all that you too, as members of the Linkerd community, can take part of our Linkerd Community Anchor Program, which means that for events like the upcoming KubeCon, if you've got a really interesting talk that you want to share, or even if you have something that you want to submit for any event like KubeCon or some other event as well. I know that Saul Roberts did GrrCon recently, which is all about pirates and technology, which is pretty neat. This is the Community Anchor Program. We will help you to develop your content, to polish your talk, to do whatever we can to get your talks accepted when you have it submitted. You can tell your story in any medium. So if you want your own blog, or if you are, any way that you want to tell your story, we will help you do that. We'll help you with the content. We've got demos on hand that we can share with you. And at the end of the day, you'll become a recognized expert. So really taking your participation in the Linkerd community to the next level. So we've got a link there, linkerd.io/community/anchor. Check that out. And you will be there to help you out with that content, the stuff that you want to share. We still have our 2021 Linkerd user survey. We're entering Q4 of 2021, which it blows my mind how quickly the year's gone by. It would really help if you haven't taken the survey, please do. We take this information and we use it to make Linkerd better. It's a short version. When people request features or they have questions about what's coming in Linkerd, this gives us the opportunity to prioritize the roadmap, or change the roadmap, adjust the roadmap, if based off of the feedback that we get. So yeah, have a look at that, and it really helps us, it helps the community, and it helps Linkerd. Okay, it's news and updates time. So I have it on good authority that 2.11 is coming. It's very exciting. The last few Edge releases have been release candidates for 2.11. So we're looking feature complete there. We just need a ton of testing. In the demo today, I will be using the latest Edge, which was released yesterday. You know that when we had an Edge released on Friday and an Edge released on Wednesday. And so when that breaks from our normal Thursday to Thursday cadence, we know that it's getting really close. So it's very exciting stuff. Please give us your help testing it and making sure that it's bug-free and that it works the way that you expect it to in your environments. Another piece of information, or some other news, is that Chris Campbell has written about his experience with Linkerd. I will put this into the chat here for y'all so that you can see what I'm talking about. It's a great article on InfoQ, very interesting, talking about the introducing a service mesh without too much difficulty. So, or without any difficulty actually. So have a look at that. And then just a ton of news around KubeCon. If you recall, for KubeCon EU, we did a retrospective, Jason and I, where we talked about all of the talks. We reviewed the videos. We gave you the lowdown for each, a breakdown of each of the topics and the main points, and made sure that you were aware of the different pieces of it, or the different work that people are doing in sharing their stories about Linkerd. And this loosely ties into the Anchor program. Some of the folks on here are some of our Linkerd anchors. But so KubeCon is Monday to Friday that week. It's a virtual hybrid event, both virtual and in person. There will be some folks, I believe William and Jason are going out along with some other folks from the team. And so if you happen to be going to Los Angeles, be sure to stop by and say hello to them. And other folks like myself will be doing the virtual part of that. So I'll be doing a presentation in our virtual booth. We will be around to answer questions. So if you're also virtual, I guess if you're in person, you could do virtual as well and ask us questions, assuming that the LA Convention Center Wi-Fi is strong enough. But that's just a joke from old QCons. Anyway.
Yeah, if you're going to be there in person, I would love to meet you. So come up, say hi. I'll give you an autographed copy of the Linkerd source code.
I have mine back here. So yeah, just these events we've got on October 11th, the crash course in MTLS and authorization presented by our own William Morgan. On the 12th at Service Mesh Con, Frederick Klingenberg will be talking about the work that they did replatforming a major retailer. The panel discussion, which I'm pretty excited about, is Service Mesh War Stories, which I assume means not service meshes fighting against each other, but service meshes working within customer applications or user applications. Wednesday, Oliver's going to give his overview and state of Linkerd, and I believe that one is virtual. And then Friday, how in Tane, Australia, 10x throughput with Linkerd with Steve Gray, who is one of our Linkerd ambassadors. So
nope.
No.
Mine's going to be in real person flesh.
Oh, awesome. I will see, this news to me. So in the flesh, you can meet Oliver and William, and I know Jason will be there and some other folks. I don't know the entire list, but be sure to stop by, say hello, and get all of this information into your brain about Linkerd. So that is news and updates. With that, we'll hand it over to Oliver for the Linkerd roadmap.
Howdy. So I don't know what we want to cover today exactly. I don't know if I'm spoiling anything by saying that Stable 211 is on its way out the door. It's probably going through CI right now, maybe, Alejandro? Excellent. Yeah, so we've got the release notes all written up and most of the first pass at docs and tutorials. And that should be available in the next hour-ish, or hopefully, assuming CI just works.
Blog post has already been published, so
there we go.
You may not be able to download it, but
yeah, so that'll be available today. And the big feature there is that we add policy. There's a whole bunch of, I mean, we've been working on this, I think, since April or May. So there's lots of small changes in there as well. We've made changes to how IP tables are configured so that we don't expose things that are only bound on localhost. We've added, obviously, all of the inbound policy stuff. We've reduced the proxy's memory and CPU usage in load tests, at least. And lots of fixes and goodies in there. So we're eager for feedback, and we'll do a 2.11.1 if we find issues in the next couple of weeks. But other than that, we're over the next few weeks probably spending some time recovering from 2.11. There's tests work to do just to make the things a little faster. CI is getting a little slow at this point. And we have some prototyping that we want to start doing to think about where we're going in 2.12. But the plan right now for 2.12, and then this is still not fully fleshed out or scoped into issues, is that we're going to start working a lot more on client-side policy. And what that probably means is figuring out how to deprecate and move forward with the replacement for service profiles. We may end up sticking around with service profiles, but we're going to figure that out. things that fall into that bucket are things like circuit breaking. In 2.11, we've introduced a new extension for SMI. The idea here is that we don't want Linkerd to have to install the SMI CRDs for you. You may have them otherwise, or you may not need them at all. And so we can use the SMI extension to read SMI resources and generate Linkerd specific resources. And so this is an adapter layer for the community that cares about SMI to get involved and work on that interface bindings between SMI types and Linkerd types. That also means in 2.12, we'll probably be removing traffic split from the core Linkerd functionality and moving more to new Linkerd specific primitives that kind of tie into our system a little better. There's some other thoughts around maybe starting to satisfy more of ingress use cases. Things we could do there are really reduce the kind of overhead of having to manage multiple hops of connections between Linkerd proxies and ingresses. We can probably flatten that out and improve that a bit. But that roadmap is still a little up in the air. And so some of that stuff we'll investigate in the next few months, and others we're going to work on and get into 2.12, which at this rate, I'm going to guess is late this year, optimistically, more realistically, probably early next year. Yeah, and so that's what's going on. There's a great time to get involved and help clean things up. We'll be doing some issue grooming and kind of trying to start putting work we have planned for 2.12 into GitHub, so that'll be a little bit more structured and hopefully easier to get involved. As we get late in these release cycles, it gets a little messier because we're just wrapping up a bunch of loose ends and not all of it's scoped in GitHub the way it probably ought to be. So that's what we've got going on. But yeah, next big step is KubeCon. So we've got 2.11 out. There's a lot of probably education to do around policies, and then we'll go to KubeCon, and then we'll start to set our roadmap for where we're going in 2.12.
Awesome. Yeah, thanks, Oliver. I'm so grateful that you're already talking about 2.12. I've just been watching this team push and push and push to get 2.11 out. I've seen a ton of work and a ton of bug fixes and features added and lots of the really in-depth architectural and technical conversations, and the team has been pushing really hard. So well-deserved break, I think, is great, and then back to pushing on 2.12. So it will be said later, but I'll be the first to say it. I think this is, and I hope it's not too early. I hope I'm not jinxing it, but great work, team. Congratulations. It's going to be very exciting.
2.11 is super cool. Like the new policy stuff is really neat. It's really neat.
So, it really is. And yeah, with that, Oliver mentioned we're going to be spending a lot of time on docs and feedback and education. And so today I mentioned that I will be doing a policy demo. So this is the first official policy demo, and I'll tell you, it couldn't have happened without, again, that larger team effort. You'll see from the docs when we release them today that there's a tutorial in there. A lot of what I'm doing here comes from that tutorial. So that was Alex who put that together. So credit to him. Oliver really helped me with these slides, making sure that I was communicating the correct information around policy. So, and then of course, the work that the team put into actually building this feature. So I feel like I'm getting the glory of being able to be the first person to share policy with you all, with the community. But again, as an open source project and just the collaboration that happens, I'm just the speaker, the mouthpiece for all of the work that's gone in. So with that, again, I'll say thank you to the team, and then we'll just jump right into this. Let's see how this goes. Oh yeah, that also means you're subject to being guinea pigs for this presentation. So let's jump right in. Policy. What is policy and why? So the why in part is because folks have been asking for this feature for a while, but also because it makes sense. If the service mesh is, if Linkerd proxies are managing traffic between services, it is a natural point to be able to control which services or which workloads specifically can communicate with each other. So what it is again, being able to control which connections a pod can accept and which workloads can communicate with each other, like I said. And it uses Linkerd's MTLS to authorize clients. So that's a big differentiator between the default Kubernetes network policy. So as Linkerd is handling the traffic, one of the main features, the first features for Linkerd 2 was the mutual TLS between the services. And so we're building on that by establishing policy as well as that secure communication. So we'll see how that works a little bit as I go through this presentation. But what we see here is a very simple example of services in a default Kubernetes cluster, even with the default version of Linkerd installed right today. There are no policies in place. So any service can talk to any other service in any other namespace inside of the cluster. So the way that this is implemented, the how is that it is cluster-wise and per workload policies. And so when we create, and I'll walk through this with you, this will make sense as I go through the demo part of this, but when we create when we install Linkerd, there's no policy in place at all. When we create what's called a server resource, that's going to enforce a deny all policy by default. And then we have to go and create these server authorization resources to be able to allow those connections between inbound for a service. So the way that this works is the proxies discover all the policies for pods in a pod's container ports. So these are port specific. Each port on a pod can have a different policy, which is very powerful. And again, I believe is different from some of the default Kubernetes implementation. The types of policies that we can have are all authenticated, all unauthenticated, cluster authenticated, and cluster unauthenticated. And those unauthenticated pieces allow for services that are not part of that are not injected with the Linkerd proxy to communicate with services that are. So that's, again, we're providing some very granular controls here, which I think is going to be pretty powerful. And so again, this service A is theoretically authorized to communicate with service B, but service C does not have that authorization. I just mentioned two terms that are very crucial to the design of Linkerd's policy: the server and the server authorization. These are CRDs that were created in order to be able to configure what is a server, what should be handling requests, and then the authorization around that. So when you have a server created, what can communicate with it? So when we define a server, and I'll show you some YAML later. I know you're excited to look at some YAML, but we can select pods by label, and this is similar to, this all uses the Kubernetes native selectors. So we've got a match expressions and match labels. And so we can match pods by label. We can match ports on those pods either by name and I believe by number. And one of the things that I think was really a nice optimization is that we can provide a protocol hint. So in order to skip the logic that does the protocol detection, you can specify that a certain workload is using HTTP2 or gRPC, and we'll see the full list of options. But that enables Linkerd to skip a little bit of logic and be able to process each request a little bit faster, or in an optimized way. As I mentioned before, when enabled, the server's default behavior is deny. And again, I'll show you exactly what this looks like as a workload rejects requests when I don't have a proper authorization in place. When we look at the server authorization, we see that it selects servers. So we'll specify a server and a client in the authorization. The server is one that's defined by this server custom resource definition. The client is based off of there are a few options that we can have. We can use unauthenticated, which, as I mentioned, is anything like another workload that is not part of the Linkerd service mesh can communicate with this this workload. There we can use client identities, which are generated by the Linkerd identity service. And then we can also use service accounts. So, and then another option is to use client network CIDRs. So a few really powerful, and I think the CIDRs is a more familiar option. So you can specify the range of IP addresses which can communicate with this, with any particular workload. So I hope that all makes sense. I think we can take a look at, oh yeah, so then in the next slide, we'll take a look at the YAML, but in this slide, we're talking about the differences between the default Kubernetes network policy and this Linkerd policy. So it's useful for enforcing Linkerd's pod-to-pod MTLS. The default network policies, Kubernetes doesn't have MTLS by default, and therefore its network policies don't take any sort of authentication into consideration. So as I mentioned before, we've got one of the core features of Linkerd is the MTLS, and then this network policy builds on top of that. So you'll get when you've got two workloads communicating that are injected with the Linkerd proxy, you'll have that mutual TLS, and you'll be able to enforce policy between those two. For now, it's inbound only. We'll be working on outbound policies. So as the request comes into a workload, that's when the authorization is checked rather than when it leaves a workload to see if one pod can communicate with another pod. And I think the inbound there is really the more important part, because that's, again, from the server-centric perspective, that's how a server can decide what can communicate with it. As Oliver mentioned, the server resources will be used as a building block for upcoming features. So if we end up changing service profiles, we'll see probably some of that functionality go into the server, but that's TBD. And we'll make sure that there's a smooth transition path for y'all to do that. And then it supports incremental additive authorization via selectors, and those are through the match labels and match expressions pieces that I mentioned. So with that, we'll take a look at a couple of the examples of the CRDs of the YAML. So here we have a server defined, and this is for emoji Voto, and this is what I'll be using in the demo in the next few minutes here. So we know that we set the namespace and the name to emoji gRPC. What's important here is we've got labels and we've got app kind internal, and we see over in our server authorization, the selector for the server is app kind internal. So this can be any label that you or another application adds. So for example, Helm adds some labels like managed by Helm. In theory, if it made sense, you could use that as a selector. What we're doing early on is adding our own labels just to make sure that, well, you know, that's what's right for our application. So that's why we do it that way. And then when we look at the pod selector, this should be similar. This should look familiar based off of, you'll see some of the match labels definitions inside of a service resource. So in this case, we're saying match labels app is emoji. And then if I were to open up the YAML for the emoji service, emoji deployment, we would see that it has label app emoji. And so that's how this server resource associates itself with that deployment and eventually with that particular workload or all the workloads within that particular deployment. The parts that are a little bit different that we mentioned early on, or when I was describing the CRDs, are that you can specify the port. And here the port is gRPC because the port name and the deployment is gRPC. That's not to be confused with the proxy protocol, which is defining gRPC as the protocol that the services use to communicate with each other. Just to be clear, this port name could have been anything like my gRPC or emoji gRPC, just the same, as long as it matches a port in the deployment, the pod spec of the deployment. So that's the server. And then when we look at the server authorization part, again, we've got the server here in the blue, and we know that it's going to match this server based off of the labels. And then we have a client. And in this case, we're saying we want the client to authorize TLS connections from any service account whose name is web. And so what this means is the web service can communicate with the emoji service, or maybe a better way of saying it in a server-centric way, where the emoji service is the server. The emoji server allows connections from the web service. So that's a lot of words. I'm going to run through a very quick demo because I think I know Eliza's talk is going to be pretty interesting as well. So I want to make sure we have enough time for that. So what I'm going to do is kick off a script. And then once that script is running to set up my environment, we'll go back and look at that slide and I'll show you everything that's going to happen in this demo. And eventually this will be in a repo that I'll share with y'all. So I've got a very simple script here. Actually, I'll go through the slide tells you what the script does. So there's nothing magic happening here. It's going to deploy a K3D cluster, just one node, very simple. It's going to deploy the Linkerd 21.9.5 edge release. It will install the Linkerd viz extension, and then it'll inject and deploy emoji Voto. From there, we'll leave it alone. It's going to, that's when we can start to add our server and server authorization resources. So I was actually supposed to talk slower to give it time to deploy here, but oh, why is my screen sharing paused? Sorry about that. Zoom share. Okay. Oh, that was weird. For some reason, my screen.
So Charles, I just want to ask, do you think we're going to have time for Eliza and for other folks if we go into the demo now?
Probably not. Probably
Okay.
not.
I know we got,
it, so.
I'm eager to see it, but I know we got a late start,
Yeah.
and I want to make sure we have time.
Yeah. So what I'll tell you all is I'll get this pushed to GitHub and I'll put some more descriptive notes in there. Sorry that we didn't get through it. Like I said, this is the first time that we've gone through this. And when I timed it, it seemed like I could get it done in time, but I definitely want to move on to Eliza's talk because she's got some really cool stuff going on there. So yeah, let's move on and I'll share this link with y'all. So Eliza, I'm stopping my share right now and then you can take over.
Cool, I'm gonna go ahead and share my screen. Let's see how well this works.
Eliza uses like a really weird line, so.
No, I'm using my Mac. I'm on a Mac right now. I just have to apparently authorize Firefox to share the screen because I have never.
Oh, you're gonna have to reboot Firefox after that, probably.
Okay, I will be right back.
It's probably because Firefox is written in Rust. Extra security. You want to quickly do the demo now, Charles?
Yes, I was talking and I realized I was muted. Let me see if I can fire this in real quick because my server is up and running. So let's
we'll
quickly
race.
share screen.
Whoever
Hopefully
gets the
that
screen first wins.
Yeah, well, I feel like Eliza's oops, that's the wrong term. Eliza's Rust version of Firefox is going to be faster than I can figure out my windows here. Okay, there we go. Okay, do y'all see a terminal?
Yep.
Hopefully, okay, great. So a bunch of things happened here without telling you what happened. Linkerd was installed here. Mojivoto was injected and deployed here. Linkerd Viz was installed as well. And just as a sanity check at the end, I did we looked at the statistics for the Linkerd Mojivoto. So what I'm going to do is apply these servers. Serve. And so again, these are just servers. This is going to implement that default deny policy. So if I do that, we'll immediately see traffic stop happening. One thing I wanted to point out is you'll see I have SRV and SAZ. These are the names, server authorization and for server for the resources. You'll see these in the labels for the metrics. And so I think it's good to know if you decide to create your own Prometheus queries for that. Okay, so what we also have is Linkerd, let's just auth z Mojivoto and I think that'll do it. Okay. So what we see here is that there's zero traffic. Okay, there's Eliza back. Okay, no traffic going through. Everything's being denied. If I were to show you the logs of the proxy, you would see that they're being denied. The traffic's being denied as well. So that's the cliffhanger. All right, Eliza, I'll hand it back over to you.
All right. Just a sec to get my, oh, am I muted? I'm not muted. Okay, that's good. I'm just going to need a sec to get my slides pulled up here. Oh, they're in the same browser window as the Zoom call. That's the problem. And all right. Full screen, right, and okay, are we all seeing my my screen? It looks good. Okay, cool. So, hi everyone. I'm Eliza. I think some of you probably already know me, but for those who don't, I'm an engineer at Buoyant, where I'm one of the core maintainers for the Linkerd proxy. As a lot of you probably are already aware, Linkerd supports transparent retries for HTTP requests to improve reliability by automatically retrying some classes of request failures transparently. In Stable 2.11, though, we are adding support for retrying requests with bodies. This is something that we haven't done in the past in Linkerd, but it's very important, especially for folks who are using gRPC. Because all gRPC requests are HTTP posts on the wire, and they have message bodies, and the gRPC message payload is contained in that body. And adding requests, or adding retries for requests with bodies was kind of a fun engineering challenge, actually. So I thought it would be interesting to do a bit of a technical deep dive in how we actually implemented this. So why isn't it advancing my slide? Hang on. There we go. Okay, so this seems pretty easy, right? You want to retry a request, you just send the body again. Well, not really. It's actually quite hard when you are a proxy, because right now Linkerd doesn't actually do any buffering of request bodies. It receives the request body from the client, and then it sends each body chunk that it receives directly upstream to the server. And we don't do any buffering because buffering, it has a lot of overhead. It's some concerns here, like we don't want to introduce additional latency into the request by waiting for the entire request body to complete, storing all of it in a buffer, and then sending it along. We don't want to have the proxy use a bunch more memory for holding the whole request body in memory. And then there are like some requests that might be very long. In HTTP 1.1, you have transfer encoding chunked, which is where the client sends potentially a very long body in multiple chunks. And those might arrive over a very long period of time. You might have, in HTTP 2, you have streaming request bodies, and those streams might be extremely long. You might be sending an entire video from the client to the server as part of the request body. And if we were buffering those entire bodies, we would have to wait for that whole body to complete, which isn't the behavior that the client might expect, because it wants to send each piece to the server and have the server do something with each chunk of data as it arrives. We don't want to introduce the latency of waiting to buffer the entire body. Similarly, if those bodies are like a multi-gigabyte video file, we don't want the proxy to store that whole multi-gigabyte video file in memory for every request that is being sent to some video server. So it's not actually that easy. And some other fun stuff, what if the request fails before the body stream has finished? What if we have sent some of the body and the server already says, oh, here's an error, and then we want to retry that request, but we haven't completed the body yet? We want to avoid doing mem copies. As we buffer those bodies, we don't want to take all of the bytes of the body and copy them all in memory, because that might be a very large amount of data to buffer. And we would prefer to not do like big expensive array copies in the request path, because that adds a lot of overhead. What if we retry a request multiple times? Linkerd supports retry budgets. So if a request fails, we might retry it. And if the retry fails, we might retry it again. So we want to be able to reuse the body more than once. And finally, what if the client's content length is a lie? What if it gives us some value and then the body is actually longer than that value? This is not standards compliant behavior. The client is supposed to return or send a body that actually matches the content length header that it sent. But if it doesn't, there might be a bug. This is also, sometimes there are request smuggling attacks. This probably matters more when Linkerd is, for example, injected into an ingress where it might be exposed to traffic from the outside world, but there's like a class of attacks where clients advertise a payload of one size and then send more data and rely on proxies doing behaviors where some of that data isn't sent or some of the extra data is sent. So there are like a lot of sort of edge cases and weird issues involved in buffering and resending request bodies. Fortunately, though, the Rust library ecosystem is here to help. So we can leverage some very high quality libraries from the community. In particular, the crates we rely on are the HTTP body crate and the bytes crate. HTTP body is an abstraction. It's a Rust trait, so like an interface for abstracting over HTTP request bodies and response bodies. And this is very important because it allows us to implement our own body types and give them to Hyper, which is the HTTP implementation that the proxy uses. The bytes crate provides reference counted shared byte buffers. And that's important because that's sort of a key component of our buffering strategy. Now, interestingly, both of these libraries happen to be maintained by Linkerd maintainer emeritus. So Sean MacArthur and Carl Lerka are the maintainers of these libraries, and they both previously worked on Linkerd. So the Linkerd community has invested quite heavily in the Rust networking ecosystem. So why these reference counted byte buffers are important, I'm going to show off a little bit about the buffer management strategy because it's sort of the key principle of how we implemented request body retries. So if you want to send a request twice, you might have some buffer in memory that represents here's all of the bytes that we received from the client for that request body. We want to store it someplace so that if we send the request and it fails, we can then send it again. So the naive way we would do this is we have some buffer. Here it's the ASCII text hello world. You see it has the length 5 and it has some bytes in it. And this is sort of a contrived example. In real life, these buffers are going to be much larger, but you know, it fits on the slide. So you want to copy this body, you clone it. For example, let's say this is the Rust standard library vector type. You would call the vec clone method. And now you have 2 of them. This isn't great. This does a memcopy, right? This allocates some area in memory that is the same size as the original buffer, and then it copies all of the data from the original buffer into the new allocation. This isn't great. It hits the allocator, that adds overhead, and then it copies all of those bytes. And if you have a lot of bytes, then you spend a lot of time copying them, and we would prefer not to do that. So with the bytes crate, here's what we can do instead. We take this vector, which is just, it's a length and some other metadata, and then is followed by like a linear array of bytes. Instead of having that, what we have is the metadata has now been expanded to include a reference count, right? And then instead of a handle that points directly at this, we have a pointer. And the pointer points at this data. And if we want to clone this data, if we want to have 2 copies of it, and one of them that we can send to the HTTP implementation to send the actual request, and then another that we can hang on to when we retry the request, instead of copying all of the bytes, we just do this. So this is the bytes type, and its clone method. You increment that reference count, and now you have 2 pointers. And those pointers point to the same memory. The reference count is now 2. So that means that we don't deallocate this buffer until both of those references go away. But we only have 1 allocation, and we're just sharing it. And so as this little star says, this is 100% memcopy free. So this is much, much faster than copying all of those bytes. You increment 1 reference count, and you copy 1 pointer. Again, in this case, it would probably have been faster to just copy the ASCII string hello world, or hello, right? Because it's very short. But in real life, they're not going to be that short. And those memcopies are very expensive. So that's cool. This gives us a tool that allows us to keep bodies around without copying all of the bytes. But what do we do when there's more than 1 body chunk? As I mentioned, we might have streaming bodies like transfer encoding chunked. We might get lots of pieces of body over time. In HTTP2, this is almost always the case. HTTP2 is a streaming protocol. So we're going to receive lots of data frames for HTTP2 that are like little pieces of body. And we want to collect all of those to get 1 body or 1 buffer. So we have some way of appending. And this is how, with the bytes crate, this is how we would append 1 buffer to another. So here we have the same bytes from the previous slide. This is like, it has a length of 5, it has 1 reference, and it says hello. And then we have the second buffer, which is the text space world, right? Like the ASCII space and then the ASCII text world. And the way we would append these is using the bytes extend from slice method. And so what this does is it extends the, oh, I did a typo on this slide. It says refs 11. It's supposed to say length 11. It increments the length, and then it copies all of those bytes from the new slice to the end. This does a memcopy, right? And it might do a malloc. If there isn't enough capacity in the array to hold all of the additional bytes, this will also reallocate. And that does another memcopy because it copies all of the bytes that were in the old allocation into the new allocation. So so this is like actually not great. So the bytes crate has these nice reference counted buffers, but if we want to add data to the same buffer, we're still doing these expensive memcopies. And it's not very good. So this is where we had to implement our own buffer management strategy in Linkerd. And what we did is we came up with this buff list type. And this buff list type is an array of pointers to bytes buffers. So here we have, this is the array, and it has a pointer in it, and the pointer points to this byte buffer. And then this, again, is the string hello. And if we want to add world, we do this. So we just push it to this buff list. And this is what's happening. We're receiving these buffers from the HTTP implementation. They're coming from network card. They're actually reading the bytes from the TCP stream. And so we have these buffers in memory where we're reading those bytes into, and they're not necessarily contiguous or anything like that. So instead of actually copying all of the data into one big array, we just do this. And we keep doing it over and over again as we get more and more chunks. And as you can see, this is 100% memcopy free. And so to wire this up, we have some code in the proxy where when a request is retryable, we use the HTTP body crate, which, as I said, lets us implement our own bodies with our own arbitrary behavior. And we implement a body that does this buffering while the data is being sent. So as we receive more data chunks, we forward them to the client. But while we're doing that, we also increment the reference count for those chunks, right? We clone them, very inexpensive. And then we push them into this buffer list. And that's also very inexpensive because we're never actually copying all of the bytes. We have one buffer that has all of the bytes in it, and we're just incrementing its reference count and storing a reference to it in this list. And then when we're retrying, we play the body back by just replaying all of the chunks from the buffer list. The other nice thing about this is that incidentally it gets us free vectored writes. We can use write v instead of the Unix write syscall to do a scatter gather where we say, hey, we want to write this data out, and we actually give the network card all of the buffers at once, and it writes them all concurrently, or it might instead of, it lets us do these vectored writes that might be faster depending on hardware and operating system support because we have these separate allocations for each chunk of data. So the way we retry requests is first we check if the request is retryable. This is, of course, like if the service profile configures retries for a given route. So that's where you would say, I want to have retries, or I don't want to have retries, or I want to retry requests that are posts, but not requests that are puts, or whatever. And then we have this content length limit, which is 64 kilobytes. If the request has a content length header that says that it'll be longer than 64 kilobytes, we won't try to retry it. And that's to limit the overall proxy memory use. We don't want to have like these really giant buffers in the proxy so that the proxy is just like really, really big and using up a ton of memory. And we would have to do that. And we especially don't want to have like no limit on the amount of data that we'll buffer. Because if we have unbounded buffering, you might want to do something like send a 64 gigabyte video file. And well, now if the proxy wants to hold all of it in RAM, it has to allocate 64 gigabytes. And so we have to have some limit. 64K is kind of arbitrary, but it seems reasonable. In the future, we might make this something that is user tunable if you really need to be able to buffer larger bodies, but it's sort of a reasonable limit. And so if the request is retryable, we wrap it in this buffering body, and then we start forwarding the request. And as we forward the request, as we receive more chunks from the client, we send them to the server, but we also put them in this buffer list. If the request fails, we retry by playing back from the buffer list. And if the if the buffer ever exceeds 64 kilobytes, then we kill it and stop buffering. So we won't try to buffer a request if the client says, hey, I have a content length of like 10 megabytes or whatever. If it's going to be really big, we won't try to buffer it. But if it ever exceeds that length that the client said it would be, just as a fail-safe, in case there's like a bug in the client where it's advertising wrong content lengths, or if it's ingress traffic from the outside world and a client wants to do something evil, we just say, hey, no, you're done. We're cutting you off. We're not going to buffer any more of this. And then we won't try to retry that request again. Finally, if we have multiple retries, we can very easily concatenate these buffer lists together. If we are sending some data and then we get an error back, and we haven't seen the whole body, we can continue buffering data as we retry it. And if this retry fails and we still haven't seen the whole body, we can continue by replaying all of the buffered data first and then adding new data to the buffer. So that's how it works. This is a feature we're really excited about because, again, it unlocks retries for gRPC, which we previously couldn't do at all. I have a slide here where I was going to ask if there were any questions, but I also know that we're a bit tight on time. So if there's not really time for questions, I can just turn it over to Charles. What time is it? I should do that. All right, I'm gonna just stop sharing and turn it back over to Charles.
Thanks, Eliza. I apologize for us running a little bit long here. One takeaway from that I hope you all in the community see, and I know some of the folks on the team see, is that I mentioned that we have a ton of, there are technical conversations that I get to be privy to, and this is a really good example of the thought that goes into building out features in Linkerd. It's initially something like retries. Oh, you might think it's easy. It turns out there are a lot of things to take into consideration, and seeing this team work together and collaborate and come up with a really refined, optimized solution, it's powerful and it's very cool. So thank you again, Eliza. That is fantastic. Yeah, and again, sorry for the shortness of time. Anyhow, let me jump back into sharing my screen. We'll get back to my slides and then we'll wrap this thing up by announcing our Linkerd hero. Let's see, where are my slides? There we go. Okay, fast forward. Eliza's. Sorry about this. Okay, questions. There we go. All right. So this month's Linkerd hero for September 2021 is your very own Ujwal Goyal. He has submitted some really helpful and creative and useful PRs, both on the website for contributing to docs, as well as code he's contributed to the website docs and raised issues to help make the docs better. He spread the Linkerd message with some tweets and just sharing his excitement about Linkerd. So we're really honored to have you as part of the community, and this is a well-earned Linkerd hero status. So thank you so much. You are much appreciated, and congratulations. Okay, and then for next month, be sure to nominate your Linkerd hero. We'll remind you of this link as the next meeting comes closer. It'll be the last week in October. No time for Q&A today. Again, sorry for running a little bit long, but thank you all for joining. I hope you all have wonderful days, and looking forward to seeing you all in Linkerd Slack, as well as in the community meetings and GitHub and wherever it is that you connect with us. So this is just our marketing slide, but that's about it. So Catherine, anything I've forgotten before we sign off?
I think that's it for today.
Okay. All right, well, thank you all. It's really good seeing you.
Thanks, everyone.
Yep. Take
Bye.
care.
Thank
Hope to
you.
see you at KubeCon. Yep. Bye-bye.
Yeah.